Good afternoon. Welcome again to the second part of the webinar. So it's a pleasure for me to co-chair the second part of the webinar 3 about the assessment and retrofitting of buildings and bridges. Let me very briefly present the next speakers. The first one is Dimitrios Lignos. The second one will be Ivan Jongo. Then Tilemachos Panayotakos, and finally Sergio Lagomarsino. All of them will address the new clauses of Eurocode 8 Part 3, respectively about steel structures, timber buildings, bridges, and masonry buildings. Let me remind for those of you who have just connected to the sections, we invite you to make questions. We will convey the questions to the speakers, but it's very important if you write the questions in the chat, and please remember to identify yourself with your name, institution, and email. Email, very important, because in case we don't have enough time to address all the questions, the speakers will respond to any remaining questions via email. So we move to the next speaker, Dimitrios Lignos from the Civil Engineering Institute at EPFL of Switzerland. His speech is about the assessment and retrofit of steel structures. Professor Dimitrios Lignos is a chair at EPFL since 2016 after a remarkable international track spanning from the US, Canada, Japan, Greece, and eventually in Switzerland. And his research involves the computational modeling, large-scale experiments for the fundamental understanding and simulation of arc-induced collapse of steel and composite steel structures. He was responsible for the revision of the steel and composite steel concrete structures in Eurocode 8 parts 1.1 and 1.2, the revision of the new chapter 9 of the Eurocode 8 part 3 for the development of the seismic assessment models for existing steel and composite steel structures. He was the convener of the European Committee Standardization for the development of the new technical specification for the characterization and qualification of structural components for seismic applications by means of cyclic tests. He's a member of different panels due to his previous academic track. So in Canada and also in the US, like an ERP consultant, and involved also in a research to practice project in the ATC and in the NIST and in the US. So I yield the floor to Dimitrios Lignos. Thank you very much for being here.
Okay, thank you very much for the nice introduction. So I would like to start by thanking Professor Rita Bento for the invitation organization of the webinar, as well as Philip Biss, Professor Ploumnier, Paolo Frankin, and Professor Kappos for extensive feedback throughout the process to draft the Chapter 9. This chapter contains rules for assessment and retrofitting of steel and composite steel concrete structures. So it follows more or less the layout that Professor Christostomou, essentially showed you earlier. So section 9.1 introduces the scope. 9.2 has information regarding identification of geometry, details, and materials. I will be more specific. Then 9.3 goes into structural modeling of steel elements. 9.4 talks about resistance and deformation models for assessment. 9.5 talks about verification of limit states. And 9.6 includes resistance models for retrofitting. In fact, there are 7 retrofitting schemes that are recommended. And again, I will talk briefly about those due to brevity. Note that this goes over 40 pages in this chapter, and obviously, you know, it's much more extensive compared to what was there before, which was much more brief if you are already familiar with the existing version. Now, please note that what I'm talking refers to the following versions: 1998-3 2023, then part 1.1 and part 1.2, that 2022 versions that have been formally voted. So there could be changes due to the response to comments, but this presentation refers to these particular versions. Now, I will, with regard to identification of geometry, geometric details and materials, the chapter puts emphasis on the identification of the lateral load resisting systems prior to the actual assessment and construction of a model, the size and thickness of connecting elements and construction of a model. This could be related, for instance, to beams, columns, as well as bracings, depending on the configuration. We should be paying attention to the particular cross-sectional member geometry and possible eccentricities between beams, column axes, as well as bracing and connections. And I'll show you a couple of examples on that could be quite detrimental. And then there's considerable information that has been added with regards to base metal and connector materials that, of course, somebody has to identify here in the geometry first. Now, with regards to details, particular attention is paid to connections that may feature welds. This is a major consideration for both bridges and buildings because for the first time there is a distinction into code-compliant welds as well as connections with non-compliant welds. And here, for instance, you see an example where the distinction is made in cases where the weld backing bar has been removed or not, and this is a typical detail that you see in construction dated from prior to 1990s, where, for instance, this particular case is known to hide potential flaws in existing welded connections, where these eventually could trigger brittle fracture. And here you see an example from such a weld where the flaw would be hidden below the backing bar and would propagate inside the weld of the column to beam flange joint with a variable height in the flaw between 3 to 10 millimeters, which of course is not acceptable if you follow EN 1090-2 or other fabrication details that you would use in a new structure according to part 1.1 and part 1.2. Moreover, a couple of other things that are important are details that relate to column-based connections and that have been highlighted, where depending on the actual details, these distinguish between column-based connections that could be exposed or embedded, and these would change the level of fixity that somebody should incorporate in the model. In particular, if, for instance, you are using pinned exposed column-based connections, a logical assumption to do would be a zero stiffness at the base, but there have been studies that show that this is not necessarily true, and in fact there could be some stiffness that could help in the assessment of the building, particularly when we are looking into drift or verifications or ultimate deformations and so on. Another aspect on details relate to bracing end connections, and in particular those used in bridges, where here, depending on the connection geometry, the verification against buckling of the gasket plate itself could vary in terms of what could be the actual buckling length to be considered. And we've seen bridges around the world that in fact have collapsed because of inadequate resistance of these connections. because here the question is, how would you actually do your check to ensure that the corresponding plates would be able to resist compressive loading. Related to bracing end connections, in case that we are looking into details where they are consistent with the new Annex E of Part 1.2, then in that case we can ensure that the plastic hinge in this configuration will actually be forming in the bracing end in the bracing member. Compared to cases where you may have eccentric bracing end connections like those that I show here, where the eccentricities here could induce bending and localized deformations near the ends, and therefore the anticipated plastic hinge is not going to be in the bracing member, but would be in the plate, as you see here in the schematic. And this could lead to rupture, as we have seen again from field observations from prior earthquakes. So here I list some examples from earthquakes in Japan, where essentially this problem is evident exactly because of the eccentricity in the connection, both for L-shaped braces as well as braces that feature hollow structural sections. And here you see the ruptures that I pointed out before. Now, with regards to materials, the Chapter 9 contains extensive information. I think this relates to one of the questions we've heard earlier for a range of materials, including the base metal that you see here, for instance, rivets, if you're dealing with riveted bridges, as well as the weld metal in cases that this should be clearly defined for assessment for welded connections. And indicatively, I'm going to show some of these tables with a reference here, for instance, table 9.3 that refers to base metal. You see that there has been a considerable attempt to categorize the base metal depending on the date of production, including cases prior to 1920, where rough iron or cast iron has been used particularly in bridges or buildings, particularly as columns. And the table provides indicative values for both the yield and ultimate tensile strength for these materials that could be preliminary used for assessment in case that no other information is available. Of course, for modern steels, there is a reference to Eurocode 3. Same for similar advancements have been done for weld metals, and the weld metal that is classified according to the construction date distinguishes between cases that the filler metal is listed in the design drawings, but also those where you don't have this type of information. In line with the same developments, there is extensive information on the default sharpening notch toughness for existing welds that could be used depending on the year of construction. And these aspects are important if one is interested in evaluating the properties of welded joints based on fractional mechanics approaches that could be simpler or complicated depending on the type of analysis you choose to do. And you see here that there are values listed that essentially allow you to consider what would be the toughness of the respective material at 0 or room temperature accordingly, depending on the environment. Now, moving along into section 9.3 that relates to structural modeling. This is a section that has been considerably developed relative to what was there before. And this section provides guidelines on how to model structural components with practice-oriented models similar to those that you saw for concrete that could inform primarily zero-length elements such as those that I show you here that I guess engineering practice could be using through access to commercial software that supports such type of models. And there is a general distinction between elements with limited ductile behavior and those with ductile behavior that you can also find in Part 1.1, Clause 7.3. In brief, these models can be constructed with a linear segment where you have to introduce the stiffness as well as strength of the element based on principles of structural mechanics. And this is followed by a post-yield segment here, And by computing plastic rotation capacities that refer to ultimate rotation, as well as post-ultimate rotation, you can actually define the properties that you need to do the assessment. Now, one thing I'd like to point out here is that steel, unlike other materials, has a considerable plastic rotation capacity after the peak. This is because the post-buckling behavior of steel elements is quite generous. And here we have provided explicit information on how these rotations can be derived. And if you are doing assessment at near collapse, this could be quite important to consider. I should also mention that the parameters for ductile behavior would be more consistent for structural elements according to the new DC2 and DC3 that are covered in EN 1990 in part 1.1. And also another approach to use here to derive these properties would be also to use the technical specification for loading protocols and acceptance criteria that was briefly mentioned before. And there is a presentation from a previous webinar that you can also see about this. Now, in brief, section 194 contains resistance and deformation models for assessment for an exhaustive type of range of elements, including beams, columns, steel bracings, links in eccentric bracings, buckling restraint bracings that have been also introduced in part 1.2, steel columns as well as splices, beam to column web panels on joints that could be weak, especially if we're dealing with construction prior to 1990s, as well as bracing and connections. Now, in line with what our colleagues from Patras, Professor Fardis had done, these resistance and deformation models for assessment rely on an exhaustive collection of data that I personally have done, but also several of my students have worked on. We're looking into at least 1,500 collected experiments on different elements that are actually made publicly available to you, as well as I will show you at the end. And with those, we can essentially have reliable resistance and deformation models for materials, connections, columns, different shapes of columns, braces, as well as joints. Now, I will briefly talk about some of those. For instance, the general approach to derive the parameters for these assessment models, assuming here I'm looking at the connection, would be that we use the first cycle envelope to essentially fit our available experiment. And then this first cycle envelope is approximated with a solid black line that you see here. And then we can extract the parameters of interest that could be the resistance or deformation, as I showed earlier. And then we can develop semi-empirical models for assessment for the previous steel elements that I mentioned. So, for instance, when we're looking at beams and columns under flexure, with or without axial load, you see now that there is a categorization of the joint type, depending on the type that you have, if it's welded or bolted, or if it's welded, what type of welded could be. But also, you can find the resistance and assessment models for cases where partial strength connections are used, such as top and bottom seat angle, bolted flange plate connection, which is typical, or even simple shear tab connections. And this comes together with expressions that can help you estimate the actual stiffness of all these connections, in addition to resistance and deformation capacities. So, for example, I will show you here an example on steel beams with non-compliant seismic weld details, where the resistance models would follow what we know from mechanics, where the effective moment at yield would be pretty much an amplified version of the elastic section modulus times the yield strength of the material, and then the effective flexural strength at ultimate would be that plus a portion here that is controlled by strain hardening. But then you have also deformation models where in that particular case that you have non-compliant seismic welds, the deformation capacities are expressed as a function of height, where here, for instance, if you have a deeper beam, that would mean that you would naturally have smaller deformation capacities, primarily because of the strain amplifications that you are going to have in the weld because of the beam heights. If you want to contrast this with beams featuring compliant seismic weld detailing, so this would be compatible with what you would do now according to part 1-2 in DC2 or DC3. The resistance model would be similar to what we saw before, but also we consider the material variability in those. But then if you're looking at the deformation models, the deformation model here would rely on a more complicated expression where somebody would actually measure explicitly the deformation capacity of cross-section based on its web and flange slenderness, but also you can combine this with other parameters that could control the deformation capacity of the member, such as the unbraced length, depending on the number of lateral bracing points that you are using, and essentially would control the length against lateral torsion buckling, but also the shear span to depth ratio that is known to control also this quantity. Moreover, as we know from steel structures, the strength of the material could influence the post-buckling and buckling capacity of the elements, therefore the deformation capacity of the member. This is, for instance, something that you consider when you do section classification. So you see that this dependence is depicted into these deformation models. As Professor Kappos mentioned, and as I mentioned here, there are similar formulas for different types of connections that could be bolted and could be partial strength that you may see in moderate seismicity zones or even low seismicity zones. And again, you would have similar expressions to construct a typical force deformation relationship so that you can do the assessment of the existing structure. Now, if you want to get a feel about those, here you see a test on an IPE 300 that was tested before with some of my colleagues at University of Naples. And here you see an indicative comparison between the existing version of the steel chapter and what has been proposed in the new version. And you see that the current version, in fact, would overestimate the plastic rotation capacity at ultimate of the element and would not acknowledge at all the post-ultimate rotation capacity. Whereas in the proposed and adopted formulation, you see that this is not a problem. Moreover, if you have ever tried to do a nonlinear analysis with a curve that looks more like the green, you might have noticed that probably you have experienced convergence problems, and this is because it is known that structural analysis programs do not like abrupt changes in stiffness, such as the green. So a model like the red one, which is basically what is incorporated in the new version, should be much more it should be much better in terms of convergence when you're going in the descending branch and you're looking at the formations at a near collapse. Along the same lines, you can also find resistance and deformation models for assessment of columns of different shapes. Here, the resistance model acknowledges also the presence of the axial load, and in particular, the gravity-induced axial load, not the transient, because it has been found that the transient component is not as significant as the gravity one. And also, the resistance model takes into account that for open sections, you may have issues with lateral torsional buckling, and the strength has to be reduced accordingly. Again, the formation models would show dependence on the web slenderness of the column, as well as the member slenderness of the column, and the presence of axial load. And notice here that these equations have an upper bound, primarily because of the availability of certain experimental data, as well as other failure modes that could be controlling, such as welds. Similarly, if you're looking into bracing elements, the particularity here is that braces would behave differently in tension and compression. In fact, the hysteretic response that you see here in the figure would be quite asymmetric. So for this reason, assessment models in this case cover two models, one for tension, the other for compression, that you can again introduce in your assessment model. And again, by leveraging an exhaustive data set of over 300 experiments, we have been able to identify pretty much some of these points. So the format here, as I said, would be for tension and compression. And resistance models, in fact, for tension would simply be giving you the axial resistance of the member by considering material variability. Whereas for compression, essentially, you have to compute the buckling resistance of the member. And here, where you have stabilization at the ultimate deformation, the 20% of the peak here is essentially an empirical value that has been derived based on data. Now, deformation models, this is an example for a hollow section, are relating deformation capacities of bracings as a function of web slenderness that is normalized with the cross-sectional limit for cross-sectional classification according to Eurocode 3. And similar expressions here exist for all types of bracing shapes, including L, hollow, and I-shaped members. Now, I know that, from almost nothing to pretty much almost everything, it could take a lot of time to digest and use some of these models. So to ease or to facilitate the ease of use for resistance and deformation models, at TPFL, we have developed a web-based interface for exploitation of the models I showed earlier, as well as the data that we have used to develop these models. You can visit the website with the QR code here, or you can also visit here. And essentially here, by browsing in the map, you could basically even go locally if you are interested about local information in Italy or Greece or US, etc. You can get essentially information on materials that have been tested on site, or for instance, I showed columns. You would like to identify tests for a particular structure you are assessing, and certain characteristics such as the axial load or cross-sectional characteristics. You can filter the data and you can download these tests. But also, if you want to link back to the resistance and assessment models I showed, here through interactive web interface, you can essentially tweak the geometric parameters of your element, the loading parameters of your element, as well as the material properties that you have. And both for built-up shapes as well as standardized shapes in Europe, US, or Japan, you're probably interested in Europe here, you can essentially compute and compare with what the Eurocode 8 Part 3 would tell you to be able to use these models relatively easily. And of course, there is information also on braces and so on, and we constantly update this. Now, before the end, I'd like to talk a little bit about verification of limit states. So as we saw, the formation capacity of a primary or secondary structural element near collapse would basically be given by a formula such as the one I showed earlier, divided by a partial strength factor that you can find in sections 9.5.2 to 9.5.7, depending on the structural element you have. And partial factors have been calibrated based on the structural element, thanks to Paolo Franchini here. One thing you may notice if you compare with other construction materials is that the partial factors for steel are not as detrimental as other materials, simply because the uncertainties we're dealing with are not as extensive as those, for instance, reinforced concrete or other materials. And this is why some of these values you would see that are much smaller compared to what you would use for concrete or masonry. Similarly, if you are looking into deformation capacity of a primary or secondary structural element at significant damage limit state, again, you would have to compute the factor ASD theta from part 1.1. And gamma RD, again, would depend on the element of interest. And the formation capacity of a primary or secondary structural element at damage limitation would relate to the yield deformation that is explicitly given in section 9.4, depending on the structural element, divided by 1.1 for primary structural elements or 1 for secondary elements. Now, note that in case that you're dealing with a non-dissipative connection or non-dissipative element, you can use the resistance model in this case that is explicitly provided in section 9.4. And gamma RD here would be considered constant and equal to 1.1 if you have no other information available. Now, with regards to resistance models for retrofitting, in fact, the chapter contains 6 retrofitting schemes you can follow, particularly if you're dealing with weld deficient details. So how can you actually retrofit welds? And what would be the corresponding resistance and deformation model accordingly? Or if you are retrofitting with stiffeners or doubler plates to enhance, for instance, elements in shear, or beam-to-column joints retrofitted with hunched stiffeners, that is a typical detail we see in steel construction. And there are also detailed sections that refer to cases where you may use an encased composite column, where, for instance, you could be combining fire protection in addition to enhancement for seismic loading. And of course, if you are working with riveted construction, there are sections and guidelines on how to retrofit riveted or bolted connections and joints. So I think I'm right on time. So I'd like to thank you very much for your kind attention, and I'll be happy to take any questions, or feel free to email me if we cannot make it to talk after this presentation. So thank you very much.
Thank you very much, Professor Lignos, for a very nice presentation with helpful insights into the important topics related with the assessment of steel structures. I'm wondering if there are questions. I can't see any questions, if I'm correct, in the chat. Meanwhile, I can make questions. There have been some questions related to bad detailing in all the structures. So I think that you have addressed very well this topic, talking about steel beams with non-compliant details.
As well as bolted connections that you may be dealing with eccentricities or plates that could induce bending, and you may think that these perform as pinned connections, and bending would potentially cause problems in the load path that I think Professor Kappos mentioned of the existing structure. And this could be quite important considerations for the retrofitting scheme as well.
Definitely. There was another question about material aging. What about this issue in steel, for instance?
Yes. So the chapter on steel, when it comes to material characterization, provides some fairly detailed guidelines on how you can acquire with non-destructive techniques material properties of an aged structure. And from some of the ongoing work we are doing here on existing bridges, for instance, built in 1970s, we see that the material is quite reliable if we know the actual year of construction, and aging would not be something that should influence dramatically our steel material, provided that we don't have prior plastification. If we have plastification, then this could be concerning, but for that, the chapter considers details regarding the chemical composition of the steel, and if we know the chemical composition, we can then make some conclusions about aging as well.
Okay, I see. Thank you. If you have further questions, you can email them to Professor Lignos. Thank you very much.
Thank you very much as well.